All right. We're about a minute past, so I think it's probably relatively safe to get started now. So thanks everyone for joining today. We've got a really great attendance already. It's awesome. So today we're going to talk about Netflix. We're going to talk about what it looks like on the network, chunks, encoding, resolutions, quality levels, all kinds of things that if you haven't spent much time digging into it, hopefully are going to be interesting and educational. For those of you who don't know, before we built Perceive, our previous product was a Netflix cache. So we, or more specifically Scott, has spent a ton of time understanding how Netflix works, both on the network level and all the way down to individual clients, like individual TVs and Rokus and phones. So it's been kind of fun to dig up and refresh a little bit of that knowledge and put this presentation together today. So with that, I'm just going to pass it over to Scott and we'll get going.
All right, good afternoon, everyone. So today we're going to be doing a deep dive into Netflix. So we're going to talk about the details of how it operates, what we can learn from it, and how that can influence how we manage our networks as ISPs. So I'm going to start with this slide. This is going to talk a little bit about the why. Why are we talking about Netflix? Why does it matter? So let's start off with some statistics. This list here is North American downstream traffic from Sandvine's latest Global Internet Phenomena report earlier this year. And so a couple of things to notice that are interesting to talk about here. So we've got different applications. You got Netflix, YouTube, Disney Plus, Amazon Prime. A lot of these are obviously recognizable as streaming video on demand. These are what we use to entertain ourselves in the evenings. And practically everything else on here, every application is also video. TikTok, Twitch, IPTV, Facebook is probably most of that's video. And another thing to notice is there's a couple of things on here that don't quite seem to fit, right? There's this one called generic quick. There's this one called HTTP video streaming. So Sandvine is conflating a couple of different things here. They've got applications and they've also got protocols listed. So I wanted to give a bit of a background on protocols and HTTP just so we're all on the same page for the rest of this presentation. So HTTP is the main application protocol used for the internet. Practically everything runs on it. Not everything, but a lot of things, web traffic. And as it happens, streaming video like Netflix and YouTube and Amazon, they all use HTTP to serve the video files that are being played. So why is that? There's a couple of good reasons for it. First reason is that HTTP is very standard. It always works. It works with firewalls. It works with NATs. It works with middle boxes. HTTP always works. So it's a good protocol to choose instead of inventing some new protocol that your firewall might discard or that there's a middle box that doesn't know what to do with it. And then the second reason HTTP is a good choice for these video providers is because HTTP has been around for so long that there are very good servers that know how to serve files at high speed over the internet and scale that. And that's a primary thing these providers need to do. They need to serve big files at high scale, at high volumes. And so they don't need to go invent that. They can put Nginx or Apache on a standard Linux box, and they can put that behind a load balancer, and they don't need to write a line of code to do that and build the bigger volume part of their service. And the other thing to talk about with HTTP is how it's evolving over time. This is going to be important later in the presentation. So HTTP 1 and 2 have been around for a while, and those run on top of TCP. Those have been around for a while. And then at some point, Google invented this protocol called QUIC, right? We've got generic QUIC here. That's a Google protocol. Google decided HTTP over TCP had some drawbacks. They thought they could do better by designing their own congestion control algorithms instead of letting the ones in the different client devices work on their TCP stack. And so they invented QUIC, which is HTTP over UDP. And that's worked out pretty well because a lot of services on the internet, definitely almost all Google services, Facebook, use primarily QUIC now. And that's been standardized in the next HTTP standard, HTTP 3. So over time, what we're seeing is a slow but steady evolution of the internet from TCP-based to UDP-based. And then I've also got this chart over here by Cisco showing that there's a divergence in the growth of busy hour internet traffic from average internet traffic. And I think what's driving that to be so large is the kind of ongoing evolution of people dropping their cable and satellite TV subscriptions and switching from a broadcast model of watching TV to a video on demand model over the internet. So primarily that's being done during peak hours in the evenings. And so that's driving this higher. And so I think this Sandvine report is pretty conservative. It's talking about total volume, but if we look at what's happening during peak hours, reports have Netflix as high as 40% on some networks. So that could be even higher than that, pretty high 20%. So this is why we're talking about Netflix. It's huge. It's a #1 protocol on the internet. It drives the networks. It drives the peak capacity. It's fantastically interesting how it works. So we've got a few slides coming up going into the details. And the other reason, as Dan mentioned, is because we happen to have a kind of a unique expertise into Netflix and into the details of it. So before we built Perseem, we had a product called Night Shift that was an in-home Netflix cache. So I don't want to spend too much time on it, but basically we shipped a router that had a USB drive and ran some software on it. It went into customer's home and they could schedule content to be loaded onto it during the night. And then during the day, when they played a Netflix show, it would transparently redirect the traffic to the local store and serve it from there if that content was available to reduce peak time usage of the internet. So as part of building that, we had to learn all the details of Netflix. We had to kind of go in there and really get our hands dirty and understand what's happening under the encryption layers that they have. So we're I think we're in a pretty good place to have some expertise and talk about this. So this webinar is in kind of 2 parts. I've got a few slides talking about how Netflix works, the details of how it operates, and then I've got a few slides after that talking about how that relates to network management and what we can learn from it. So let's start by talking about what is actually going over the network when Netflix is sending video. So Netflix has been streaming video since 2007. That's 15 years. And since that time, there's been a lot of evolution in the industry. There's been new devices coming on. There's been new hardware. There's been great advances in video encoding technology. So you've gone from things like WMV and ABC into like newer encodings like HEVC and more recently VP9 and AV1. And all these new encoding standards do a better job of compressing video and they get built into newer devices. But Netflix still has to operate on those older devices that have been around for 15 years as well. So as a consequence of that, every title in Netflix has to be encoded in every one of these container formats. And I don't think I've listed them all here, there's more. At the same time, different devices can play different resolutions. So your phone might be capable of a lower resolution than your TV, and your older phone might be, or your older TV might be capable of an even lower resolution. If you still got a Wii, then you're playing Netflix on it. It's standard def at the most. So in addition to encoding every title in every one of these encodings, Netflix also has to encode it at these different resolutions. And Netflix calls this a bitrate ladder. And not only are there different resolutions for different device support, but there's also different resolutions for different network support because some networks or some internet plans obviously can't support the higher resolutions. And during periods of congestion, the network, even if the plan supports it, may not be able to support it. So back in 2015, every video in Netflix was encoded at exactly this set of resolutions. They basically went and watched a bunch of videos and figured out what bitrate most of the videos looked good at in the worst case. And then they went and encoded every video in the Netflix catalog to that. So if you were playing 1080p at the highest resolution in 2015, you were for sure using 5.8 megabits to transfer that over the network. Then in 2015, they came up with this idea of per title encode optimization. And so they actually analyzed each title separately and tried to figure out where should we encode it at the different resolutions. So maybe for the high res, we can encode one here, which is pretty good. And then we'll have one with the optimal quality over here at the cost of quite a bit more bit rate. And so each one of these gets its own resolution, its own bit rate ladder per title. And then more recently, for the newer encodings, they're even doing that on a per segment level. So they might have the 3-minute chunks of a video title, and they're encoding each of those in different levels. And I guess just to talk a bit about the reason for that is that different videos are some videos are more compressible than others. So if you've got a cartoon, it's it's a pure white background with drawings on it, very easy to compress from frame to frame. It results in a much lower bitrate video than, say, an action film, or me sitting here with slides is pretty low bitrate. But if I start waving my hands around, that's causing a bit more work to compress. It's going to result in a bit of a higher bitrate. So I guess the consequence of this on the network is that today, if you look at a Netflix stream playing over the network, let's say you watch a Netflix video at home and you're looking at what's the sort of average bit rate of that on the network. There's really no correlation between that bit rate and the quality or the resolution of what's being played. Slide. All right. So now we're going to talk about how the content goes over the network. So I'm going to say this a few times, but streaming video like Netflix it's not actually a stream. It's not a stream at all. It's a file download, just like any other big file being downloaded. And the file is downloaded into this buffer chunk by chunk. And when a Netflix player, like your phone or TV or your PC, wants to play a video, what it's doing is it's simply taking the next video segment from an internal buffer, and it's decoding it, and it's putting frames on a screen for you to watch. And the interesting part about this is how the buffer is filled from the network. So when you start playing a video, your player device will authenticate with Netflix. So Netflix knows who you are and what plan you are and what the device is and what its codecs it's capable of playing is. And then Netflix will send back in response a manifest file. And the manifest file has that bitrate ladder. So it has every rung on that bitrate ladder. And for every one of those bit rates, it has a list of 3 URLs that you can go to download video. The player can go to download video. And those URLs are chosen based on the Netflix CDNs that are closest to you. So that'll be based on things like BGP distance. We'll talk a bit more about that on the next slide. And then your player will go out and try some of those links. It'll select a resolution on the bitrate ladder to start with. It'll go probably connect to all of those 3 CDN nodes. It'll download some video and it'll figure out which one it likes best. And it'll use 1 or 2 of those to continue downloading chunks into the buffer. Video is downloaded using HTTP over TLS. And that means the video downloads can't be inspected on the wire. So nobody except the player and the server knows the contents of that. Here's kind of there's an example here of what it actually looks like if you do decrypt it. So you can see this in your web browser if you use the debug tools. It's basically asking for a big obfuscated string that the client knows how to interpret, the server knows how to interpret. It's got a host, which is this netflixvideo.net somewhere in Miami, I think, for this one probably. And it's a chunk request. So it's requesting this usually a few seconds chunk of video at a time. So video traffic, as I said, it's encrypted. That matters. The reason that matters is because that means no one in the middle can know the content, the resolution, the codec that's being downloaded. That didn't used to be the case, by the way, like way back in the early 2010s before Netflix used TLS. There were ISPs that could kind of catalog what content their customers were watching for whatever purposes they wanted to use that for. And so Netflix switched that all to TLS over time, so that couldn't be done anymore. Netflix traffic, interestingly, is actually doubly encrypted because it's the actual video is DRM encoded when it's encrypted, and then it's also encrypted at the network transport layer. And then the last point on this slide is because there's NAT here in the home usually, the consequence of that is that on the network, you really can't tell how many devices are concurrently playing Netflix. We talked about the bitrate being variable, and the number of flows is also variable. We'll talk about that coming up. And so you really can't tell on the network, we know it's Netflix, but is it 1 video being watched? Is it 2? Is it 3? Is it 4? really no way to tell just by looking at the network. All right, so one way Netflix is very interesting and different than other video streaming services is that Netflix traffic comes from many different places. You can't look at a Netflix download and look at the source IP address and say, oh, it's a Netflix AS, therefore it's Netflix. And you can't even say, oh, it's AWS, it's a public cloud. No. The Netflix traffic looks kind of like peer-to-peer traffic if you analyze it that way, because it's coming from a variety of different ISPs, address space, and sometimes from internet exchange points that are relatively close to the client that's watching the video. So Netflix has this big Open Connect cache farm. And if you're an ISP that qualifies, which is some sort of, I think, overall bit rate, the level that you've achieved, you can call up Netflix and you can say, hey, send me some Open Connect servers, and they'll ship you some servers. And you can provide the rack space and the power and the cooling for those. And then Netflix will send you a whole bunch of content to fill those in the middle of the night. And your subscribers and other ISP subscribers that are relatively close to you will serve their Netflix from those caches on your network. So main points on this slide just being that Netflix can't be detected by the AS it connects to. It's hard to predict what server a client will connect to. It's these are things that shift over time. And because these servers are being mainly managed by other ISPs, as they adjust and make changes to their address space and their data centers, those IPs may change. They may add new servers, they may remove servers, they may readdress them over time. This is openconnect.netflix.com. If you want to know more about this, you can go here. These pictures here are just pasted from their architecture document. This talks a little bit more detail about what happens when a play request comes in. But basically, it's just cataloging all the servers, where they are, what content's on them, so it knows how to build URLs to send back in that manifest. Okay, this is a debug screen from a browser-based playback, and there's some interesting things going on here that we can look at. You can do this yourself. You can try this at home. If you play Netflix in a browser and you press Control-Alt-Shift-D for debug, it'll bring up this screen, show some useful information that we can talk about. So one thing to notice is that Netflix uses a large buffer. So this buffer size of this video playback is 125 megabytes, or in seconds for this resolution, that's about 220 seconds. So Netflix is buffering almost 5 minutes of video when the buffer's full. And that allows Netflix to handle network outages and network degradations without interrupting the user experience. So if something happens, or the CPE restarts or something, it doesn't matter. The user still keeps watching Netflix and it'll just recover seamlessly from it, which is great. You can see the throughput level here. So this has two bit rates. It has the playing bit rate, so it's playing 720p at 4 megabits, and it has the buffering bit rate, so it's buffering 720p also at 4.4 megabits. And sometimes this is not the same. So there's a couple things that can happen. So if the throughput, so this throughput is measured by Netflix as it downloads bytes. Let's say that throughput went below the level of the video, and it did that for a while. So Netflix is starting to get worried that that buffer is not going to be able to stay full. So what Netflix can do then is it'll start a new buffer. It'll go down the bitrate ladder. It'll climb down that ladder. So how it does that, it kind of varies. It may go down to the bottom and start climbing back up, or it might just shift down a rung. That's a proprietary algorithm in Netflix, but it can start a new buffer, start loading it with the lower bitrate video, and then sometime after that, the playing bitrate will change to the lower bitrate video. That's called a downshift. And when that happens, you can notice it if you're watching it. You've probably seen it if you watch a lot of Netflix. The picture will just, it's a frame by frame change, so it doesn't go black or anything. But the next frame is just a little bit less sharp than the previous one in a downshift. So not the end of the world, but definitely noticeable. And then the opposite can happen as well. If Netflix suddenly detects that the throughput's gone up a lot and it thinks it can play a higher resolution video, it can switch the buffer to start buffering at a higher bit rate, and it can do an upshift up to that higher bit rate. And again, that's going to be noticeable. The picture will just get a little bit sharper. And so the details of that algorithm and how it works are proprietary to Netflix, and it can change as they do more research. The goal they have, obviously, is they want to maximize stability, so they don't want a whole bunch of upshifts and downshifts. So stability is important. Quality is important. They want to play the highest bitrate video that the network will reliably support. And as an absolute primary goal, they want to make sure that buffer doesn't starve, because if that buffer starves and goes down to 0, then you get the spinning wheel of death. Nobody wants to see that. You don't want to see that. Your subscribers don't want to see it. You don't want your subscribers to see it because they might call you about it. So Netflix has lots of algorithms in place to prevent that from happening. One last thing to say here. So an interesting result of this upshifting and downshifting behavior for WISPs is that if you're using bursting, it could cause Netflix to misestimate the throughput when a video starts. So it can work like this. Let's say you've got a 10 megabit plan and you've got it configured to burst up to 15 megabits. So when a subscriber starts watching Netflix, let's say they got a 4K TV and they're playing a title that's encoded at 12 megabits. So Netflix is going to say, "Oh, I can download at 12 megabits, no problem. I'm going to start playing 4K." And then once that burst interval ends after a minute or two, all of a sudden, that throughput, Netflix detects the throughput's gone down to 10 megabits. It starts to starve out that buffer, and it says, "Oh, I better downshift to a 1080p version instead." And so there's a downshift, and basically it's just it's not a huge impact on the subscriber, but it was a waste, right? The subscriber didn't need to be watching that 4K video when the plan actually doesn't support it. So bursting does not help with Netflix. If anything, it hurts things a little bit. All right, this is kind of a geek slide. This is a Wireshark slide, but this is really important. Now, there's a couple of points I want to make here. So what this is showing is it's showing bitrate over time at very high granularity of a Netflix stream that I played on a TV. This is I think the streaming session was about 5 or 6 megabits, and there are 3 flows being used, so 3 TCP flows being used to deliver this video. That's how this TV happens to behave. And I've highlighted those 3 flows using colored lines here. So I've got red, a green, a blue, and then this black line is the sum. So this is the overall bit rate being sent over the network. So this is what I mean when I say Netflix is not a stream. Even though it's called a stream, it's not a stream at all. It's a download. So this is not streaming at a fixed bit rate of 6 megabits. It's actually going at about 40 megabits here to do an initial buffer full. And then we got 0 megabits for a little while it plays some of that buffer. And then after that, it's kind of spiking up between 15, 20, 25 megabits and 0 as it downloads segments over time to keep that buffer full. And we've got these 3 flows. It seems to be dividing it pretty much equally between those 3 flows as it keeps the buffer full. This is one device. This is a smart TV, and this is on one network. So behavior of how Netflix does this can vary with different devices. It can vary with network conditions, and it can vary over time as Netflix does more research and changes these algorithms to work better. I don't know this for sure, but I suspect what they do is they test what works best on each device, and then the software for that device uses that approach. So for some devices, one flow might be better. For some devices, 3 flows might be better. And on the next slide, we did some experiments in our lab fairly recently just to get a sense of kind of how much this varies across different devices. So Android phone, we only saw 1 flow for the entire stream there. Same with the Sony TV that probably runs some version of Android under the hood, 1 stream. The Samsung 4K TV, we saw some playback where it had 3, and some playback where it used 4 streams. The PC browser seemed to use 3. Windows app used 1. The iOS devices use 3 flows. So there's a variance in how many concurrent TCP flows Netflix uses to download the video that's playing back. This is one experiment. These may be different. You may get different results if you try this, and these can change at any time if Netflix decides to change it. Also, these for the ones with multiple flows, sometimes I saw them connect to different CDNs. So there'd be 3 flows, each to a different CDN endpoint. Sometimes they'd all be to the same server, or sometimes they'd be to one or more, to multiple servers on the same CDN. So that varied pretty widely as well. Okay, so that was a deep dive into how Netflix works. Other streaming protocols that aren't Netflix use similar technology stacks, but there'll be differences. Yeah, maybe they use different numbers of flows. Maybe they're on a public cloud or their own data center versus the sort of peer-to-peer approach that Netflix uses. They may use different codecs or different types of bitrate ladders, probably. So that gives you a background, and the next few slides are going to use that knowledge that we've learned to try to draw a few conclusions about what this means for network management policies and for QoE management. So this slide shows 2 scenarios that look the same on the network but are very different. So you've got one household here. It's got a smart TV. This is kind of like the Wireshark video that we just saw. So he's doing a 4K stream. It's running at 12 megabits. It's using 3 flows, each split evenly, so each one of them is 4 megabits. So on the network, this looks like 3 TCP flows. They can be identified with Netflix if you've got DPI to do that. And the total throughput will be 12 megabits. Okay, household B. So in this household, we've got 3 devices. They're each using 1 stream per Netflix video. And you've got a TV watching 1080p here at 6 megabits. And you've got a couple of mobile devices using 720p at 3 megabits each. So on the network, what does that look like? It looks like 12 megabits and 3 TCP flows. So looks pretty much the same on the network. So let's say we wanted to try to use some tool like DPI, and we wanted to have some policy on our network packages that say, during peak hours, you only get 1080p, and we're going to enforce that. Okay, so how would we do that? So DPI basically gives you 2 tools for this. It gives you a per flow bitrate cap and an overall per user bitrate cap. So let's start with per flow. So this 12 megabit video has 3 flows. So maybe if I put a 3 megabit per flow limit on it, that would work. Yeah, I think that would work, right? So now it's only going to have 9 megabits. It's not going to be able to play this 12 megabit 4K video, so that'll probably restrict it to 1080p. Sounds good, right? But now what about this guy? Probably not a good idea, because now this 1080p flow that needed 6 megabits on one flow is going to be restricted to 3 megabits. And so you haven't delivered that 1080p experience that your policy promised to do. So that doesn't work. All right. So let's try a per user limit. So how about if we set it to 8 megabits total? Seems like a good number. 8 megabits is pretty much always going to be enough for a 1080p stream. So that works okay for this, right? 8 megabits. It's going to split these 2 streams into about, these 3 streams into about 2.6 megabits each. Okay. But now we run into problems here because we've clamped this down to 8 megabits. So you've got to split that between 3 devices. So again, that's going to be sort of on average 2.6 megabits each. So these ones are going to struggle to get to their 720p video, and this one is definitely not going to be able to play that 1080p anymore. So the point of this kind of contrived example is just that this is overly simplified anyways, because as you know, it's Netflix's variable bit rate. So there's going to be all kinds of different bit rates for different resolutions and different titles. So basically, any vendor that tells you that you can restrict Netflix playback to a specific resolution, it's just not possible. You cannot control the resolution of your subscribers will get, or the quality they will get, and you cannot control the number of concurrent streaming sessions that they'll get. All right, so let's talk about another use case. This is kind of a cool one I like to talk about. So one problem that's really obvious from that Wireshark graph I showed you is that Netflix has a potential to really cause some problems, right? When that buffer's filling and Netflix is up at that 40 megabits in that example fill rate, that's potentially going to impact other protocols that are going to be running concurrently with it. And that could happen at any point of congestion. So it can happen for the user, so they can be self-congesting their own plan with Netflix, or it could happen upstream at like an access point or some other shared point if that's filling up the capacity of that AP. So here's the idea that gets proposed sometimes. Why don't you buy a DPI middle box and just configure it to limit Netflix so that there's headroom left for other traffic to run as well. So just don't let Netflix use all the plan, or don't let Netflix use all the AP. And then you can tailor that again to operate at peak hours. So you're only impacting traffic when subscribers actually want to watch it. So basically, the idea here, which is a cool idea, is Netflix, as we've talked about, it's not a stream, but what if it could be? What if we could apply some policy to make it like a stream? What if we could shape it so that a 6 megabit video is shaped to 7 megabits, and it kind of does work like a stream, and it doesn't have that adverse impact on the network? But the problem, as we've seen, is there's really no way to know where to set that limit. We don't know what the variable bitrate encoding is going to be. We don't know how many concurrent streams there are going to be, or how many streams are playing in a household. So there's really no way to tweak that policy to do that. And the second problem with this DPI-based approach is just the overall problem with DPI. So DPI works by applying application signatures to traffic. And application signatures can be brittle. As applications change, signatures have to be updated. As new applications come in, signatures have to be added for them. So if you're going to have a policy that applies to streaming video, well, what if it doesn't identify one of the streaming video providers? What if there's a niche provider that the vendor hasn't added yet? It's hard to make that consistent, and it's hard to make it stable. So this is probably really hard to read, but I've pasted just a little section of the DPI signatures file. This is from NDPI, which is just a open source DPI engine, and you can see there's some Netflix signatures here in the middle. And from a DPI point of view, Netflix is pretty trivial to recognize, and the signature for it hasn't changed in a decade at least. And the way Netflix is recognized, as you know, it's TLS encrypted HTTP, and TLS has this really nice feature where you have this thing called the server name indicator that goes at the beginning of the SSL handshake between the client and the server, and the client says, "Hey, this is where I'm going. This is," or effectively, this is what the application is. So Netflix is putting in that handshake netflixvideo.net or one of those other domains, and then for a middle box that's doing DPI, it's very easy to inspect that and say, "Oh, this is Netflix." So that works well today. It may not work well tomorrow because there's this new standard called TLS 1.3 that introduces a way to encrypt that SNI. So basically, it's possible to send that traffic in and not have any content matching way to identify it. And as we know, as Netflix is a pretty distributed system, it would be pretty hard to identify it by where it's going. You can't just say, "Oh, it's going to the Netflix AS, therefore it's Netflix." So there's a real risk that Netflix and other streaming video applications become very hard to detect in the future. And you saw that on the first slide where I had that Sandvine report, which had like unknown quick as number 4. You know, that's basically traffic that Sandvine is unable to classify into anything more than this is the application protocol running. It wasn't able to classify it to an actual application. And so I don't know if Netflix is going to implement TLS 1.3 and take away the ability for DPI boxes to inspect it. I don't know if Disney Plus is going to. I don't know if different protocols are, but one thing that's for sure is that there is a trend towards greater privacy and greater encryption, and some video providers are going to do it, and maybe Netflix decides to do it. And the day Netflix does that, it means 20% of that DPI report just sort of goes poof. We don't know what that is anymore. We can guess some things by behavior, but we don't really know. And the big DPI vendors realized this long ago. This is a 2010s thing, right? It's using DPI to manage applications. The DPI vendors saw this coming. There's been a lot of consolidation in that industry. Dan and I both used to work for one of the leading DPI vendors, so we're pretty familiar with this. And those DPI vendors they've been buying each other out. They've been going into other industries like enterprise security and mobile charging to try to de-risk that. And then the big tier one providers that used to buy these DPI products have really stopped using them for any kind of policy enforcement like this, because there's network neutrality legislation and the rise of encryption makes them pretty wary of using DPI for network management. So, okay, but so we're back to the problem that we started with, which is how do we prevent Netflix from taking all this capacity? And luckily, the answer came along in the 2010s also, and it's this new thing called AQM that you may have heard of, things like FQ-Coddle and Cake. And what these technologies do is they solve this problem of one protocol crowding out others in an application agnostic way. Doesn't matter if it's Netflix or web browsing or gaming, doesn't matter if it's TCP or UDP or ICMP, everything gets its fair share of the network. And as a result, the interactive traffic feels fast, even when the queues are full of Netflix traffic. I'm not going to go into much detail about this. If you have any questions, we can at the end, or there's certainly other webinars to talk more about that. Presium provides a solution for this. Other vendors do too. This is the way of doing network management in the 2020s to solve this problem. Let's talk about another network management solution. So there's this concept of a TCP proxy that can make TCP work in different ways and measure different things on it. And one of the applications of a TCP proxy is called TCP acceleration. So let's talk about whether TCP acceleration makes sense as a way to manage Netflix. Can it help with Netflix quality? Well, it probably can if helping with Netflix quality means helping the Netflix buffer fill faster at higher resolutions, because TCP acceleration is going to make TCP go faster. It accelerates it. And if Netflix goes faster, it can fill buffers faster and then play higher resolution video. But when the network is congested, that extra acceleration comes from something else. And what it comes from usually, since you're accelerating TCP, is the other things that were taking up this much, and now TCP is bigger, so they're taking up this much, and that's UDP traffic. And UDP traffic not only includes traditional things you think about like gaming and voice over IP and real-time webinars and that type of thing, but it also includes things that we kind of think about as being TCP, like things that are based on QUIC or HTTP3, like YouTube and Gmail and Facebook. These are predominantly UDP based. So if we're using TCP acceleration, yes, we're making Netflix faster, but we're also making interactive applications slower. So since the previous two slides were about how can we manage Netflix and maybe make it a little less impactful, it doesn't seem like TCP acceleration is maybe the best idea, because making Netflix faster is probably not something we really want to do. Look, Netflix has its own algorithms for dealing with network congestion. We've talked about them now. It has large client-side buffers. It can shift down that resolution ladder if it runs into trouble. We don't really need to do extra things to help Netflix have a lot of the network. And I guess the other thing related here, kind of related to TCP and Netflix, is that it's likely, I don't have an official word on this, but it's likely that Netflix will migrate to UDP, being UDP based as HTTP3 becomes standard. It's a direction a lot of applications will go as those web servers like Nginx and Apache can handle HTTP as just kind of a normal configuration. And it's likely that at some time in the future, Netflix ends up going there too. So this is my last slide. We've learned a lot about Netflix. We've learned a lot about implications for it on the network. And so some of the conclusions we can kind of draw that we've talked about. Netflix uses multiple TCP connections and it uses TLS. So it's not possible in the network to limit the number of devices or streaming sessions. Netflix videos are variable bitrate encoded, so you can't limit resolution or video quality with network policy. Netflix downloads in short bursts at full link rate, which can negatively impact other traffic. And AQM technologies such as FQCODL and Cake can prevent this from using more than its fair share of the network. And so kind of the overall message that we want to get across is it's really good to manage the congestion of the network and not manage the individual application. Netflix can manage itself just fine. If you maintain a clean network that is fair to all protocols using AQM, then you're going to provide the best quality of experience for your customers.
Great. So we try to keep these around 45 minutes, so we won't go too much longer, but maybe just to round that out a little bit. When you start application specific things, they can seem like an easy button, but as Scott indicated, it really does kind of set down a path of being brittle. Like if the network requires, as an example in this webinar, Netflix to be limited to function properly, the day Netflix flicks that switch to UDP, all of a sudden the network is crushed. Like it doesn't fully solve the problem. And I think that kind of, ultimately is why, our point of view is exactly said, like managing the congestion is the real source, the real way to handle this. Because if you can manage that congestion, it doesn't matter what the application is. The customer is going to get a good experience. And those long tail video providers, there's a lot of them out there and many more than it may seem at first, right? So not everybody's is using Netflix. From our standpoint, we spend a lot of time building tools to help operators be proactive to add capacity and understand how they can deliver more bits to their subscribers, not fewer. That was something we kind of recognized a couple of years ago, that most of our customers were struggling to proactively manage the access points and the individual customers on the kind of like the RF level to deliver as much capacity as possible. And that's why that's possible. That's why we spent so much time in the last couple of years on the data side, on the scores and solving that problem, because that's 80% of quality of experience. Traffic management and trying to limit individual applications, which, as we talked about here, is brittle in the first place. But any type of artificial reduction in capacity is a mitigation to a problem. It doesn't actually solve the problem. So we've been very focused on that kind of 80% of the problem of managing the capacity with what we think are the right features to manage the congestion side of things as well. So I'm not going to go into too much more detail on that, but I guess summarizing this a little bit more, it's networks that are optimized for particular applications, or worse, particular transport protocols are very brittle going forward. And we just generally don't think that's a good plan. So with that, we've got a couple minutes left. If anyone wants to drop a question in, I can read out a couple of the ones that we've answered, just in case people aren't following along on the question tab here. So there was one question about can CDNs change midstream from manifest to manifest? I think what you mean there is can a single stream go to different CDNs? And the answer is yes. Like it'll download different chunks from different CDN nodes. Definitely can happen. Are WISPs using Perseem to truly serve Netflix subscribers? Absolutely. And again, it's we can go into this in much more detail. The key is not to manage the application; it's to manage the network. Next one, when a download starts, so they remain on the CDN. Sorry, that's kind of like the previous question as well. Yes, they can bounce between CDNs. And a couple questions about Roku, Scott. I know we did a ton of stuff with Roku's back in the night shift days. I don't know if you had a chance to look at what they do currently.
Yeah, we didn't test that one specifically, but it's yeah. I don't know offhand how many streams they use or anything like that, but it works similar to other devices. They've got their own application, so it's not one of the ones we tested. But if you do test it, I'd be interested to hear what you find.
I think the key thing there is what Scott mentioned earlier. Netflix is going to do whatever makes Netflix better, right? So
Yeah.
the reason they're using multiple TCP connections is because they can get more throughput. They're not doing it because it's fun. Like it. So if it works on one client, it's likely a behavior that exists across many different clients. Is there one streaming device that's more efficient than the others? I'm not sure that we would know the answer to that right now.
So
Certainly,
generally speaking, though, it's gonna be something that's newer because those newer
mhm,
codecs are more efficient than the older codecs. So
yeah.
if you go on a modern web browser on a modern laptop and try playing like a Netflix stream and it'll probably play at 720p or something, and you will be shocked at how little bitrate it uses compared to some of the things I've been talking about in this presentation. Like it'll use under a megabit in many cases. And back in 2015, you saw that bitrate ladder. 720p video would have been 3 megabits. So there's been amazing gains in the video compression technology over the years, and so a TV that you buy today is going to be more efficient than a TV you bought 10 years ago on the network.
Which makes it interesting to think about what would that bandwidth curve look like if Netflix hadn't made those encoding changes. It would probably be even like far worse.
Yeah, you can definitely depend on Netflix to do what's best for Netflix, and so using bandwidth efficiently is good for Netflix, but only if it's not at the cost of quality.
Mm-hmm. And you mentioned as we went through too, like they are really optimized on that quality dimension, and they do a really good job of it. Like if the network is consistent and delivering, like Scott mentioned, that bursts, which confuse Netflix and stuff. But if you're delivering a consistent amount of throughput, it's pretty amazing the quality level that it can achieve in small bit rates. And back to Scott's point about the new codecs, make that possible. Like they are highly incented to make that quality as good as possible. A question about mitigating local interference. Yeah, that one is not something that we're really too involved in terms of like what's happening with traffic within the home. Certainly, an area we'd like to explore in the future. You can see the impact of that in our metrics because we measure the actual the traffic from the individual subscribers. But yeah, someone who's got a Roku on the far side of the farm trying to come all the way back to an AP and getting a poor experience is definitely a real challenge. That's unfortunately not something that we can help a lot with today.
So I guess the next one: do Apple, Roku, Google work alongside Netflix to optimize their devices to provide the next best possible experience to users? Generally, Netflix is testing on different devices, and we're working with those other vendors in general. From what I know, I don't have firsthand experience. So.
Another question about load balancing. The only thing to be careful. So sorry, the question is: does load balancing, LACP or XOR affect quality? The only thing to be careful with there is make sure that it's per flow load balancing, not per packet. Because if you're doing per packet, the flows are reordered when they arrive at the client. And you'd see that in our metrics as TCP retransmissions, because we can't distinguish a reordering from a retransmission. So that's the important thing. Outside of that, if it's flow load balanced, yeah, should make no difference at all, other than there's more bandwidth available. But we do see that, like occasionally we'll see a customer suddenly with a ton of TCP retransmits, and it turns out to be a badly configured bonded link. All right. Well, we're up at, maybe we got one more. Scott, there's a question there.
Yeah.
Bit
So
rates.
if we offer a 15 megabit plan, just about the bit rate of 4K video, it'd be better to offer a 20 megabit plan so it does not create a double buffer for the 1080p. So Netflix is going to try to prevent that from happening anyways. I don't think kind of more back to the point, right? Like you shouldn't try to base any policy on what you think the video of Netflix is. Like all 4K videos aren't 12 megabits. Some are more, some are less. That's going to change over time. Netflix is going to figure out how to do the right thing and provide a good quality. And then if you go to the next step and do a AQM based shaping on your network, then that's going to prevent Netflix from congesting, from letting a customer self congest or congesting an access point.
All right, and what's probably going to be the last question because we're up at 50 minutes. So a lot of network users, a lot of networks have MikroTik Red OS, and you say FQ Coddle and AMQ makes the most sense. It does. So that can be a solution in some cases for sure. You know, on the client side, like even in the home. But there's another level to think about as well, which is the congestion outside of just the subscribers plan. So back to the access point and, you know, upstream from there. So we'll have some interesting things to say about that in the next couple of weeks as well. Obviously, you can go in and you can just configure access point shaping rates inside Perseem today, but that's yeah. So is there a way to segue into how Perseem? Yeah. So I guess I'll go in there a little bit. Essentially, it's about managing the congestion, like the properties that we want to enforce, or as the industry, I think we want to enforce, is you have flow isolation within an individual subscriber so that they can't self-congest. You want to make sure that one individual subscriber can't hurt other subscribers on the access point. And we configure shapers on those levels to make that possible. The access point shaping and down to the individual subscriber. So that's what we believe is the best solution to this. And again, it's you know, one dimension of best there is not being brittle to sudden outside events that break the world. That's very, very important for long-term network management. Is there any difference between Netflix's model of streaming and IPTV? Yeah, well, so traditional IPTV, so I can speak to this a little bit from past lives. Traditional IPTV within a service provider is going to be multicast based. And that is a very different beast than this. That is like UDP streams, you know, through the multicast tree within a service provider. That's more what you think about streaming in terms of its behavior. Very, very different than chunk downloads over HTTP.
Yeah, I don't know if the World Cup stream would have been using multicast. It kind of
Oh,
that.
sorry. Yeah, sorry, I didn't read the last part of that. Yeah, if it's going over the public internet, it's using. It could still be UDP streams, like the original kind of first video type applications. It's possible, but certainly like when I think of on deck IPTV, I think of like the multicast and the VOD servers and those kind of things, and that's very much a UDP style stream that people often confuse with Netflix.
Yeah, I mean the bitrate it needs, as we talked about, it depends on what it's using for video compression, what codec it's sending it at. It's maybe for the World Cup, it's totally possible that there could have been congestion on the internet side somewhere too, like maybe at the server.
Great. Well, thank you. We had very, very good attendance for that. Thanks for the great questions. If you have any other questions, feel free to send Scott or myself an email. I'm happy to talk about this stuff, you know, even outside of the kind of whatever day job, Perseem context. This is stuff that's very interesting to us. So we're always happy to talk about it. So thank you everyone for attending.
That was a lot of fun. Yeah, again, if you have any comments, just email us, Scot@perseem.com, Dan@perseem.com.
Great. Thank you, everyone.